Alright, let's look at back. Okay, so before this, on last Sunday, Sunday, we have discussed. Oh, sorry. Let me put my pen. Okay, so we have discussed 4.1. And how we have already know how to calculate the Reynolds number. Okay, equal to the rho times the velocity times the diameter over mu, the dynamic viscosity. Okay, and today we will look in second subchapter, which is the losses in piping system. And because next Sunday we have a public holiday, kan? Okay, we are holiday, so your miss there is class on Sunday, so we will miss that. Okay, so for today I will try to cover 4.2 and 4.3. Okay, so next week you have only one class with me, so we can cover the last chapter, so that, and then we can do the tutorial lah. Okay, because we miss our class on Sunday, kan, because of the holiday. Okay, alright, so this so we have done this, and you know how to calculate the Reynolds number to determine whether it's laminar or turbulent. Okay, after that, okay, after we understand and know how we can determine that, in the piping system, as we have discussed earlier, there will always a losses, okay, due to the frictions or due to the fittings, the bands, the valve, or whatever, everything lah. So we will have losses in the piping system. Before this, in chapter 3, when we discuss the Bernoulli equation, we assume that there is no losses, kan? Is it right? Can you remember that?
Yes.
Okay.
Yes, sir.
So we understand that in real life, okay, actually there is a losses. Ada, confirm akan ada losses lah. Okay. So that's why we in this chapter 4, we will take that into consideration. Okay, as there is a losses in the system, so we need to calculate this, the losses, and then we will use back the Bernoulli equation. The Bernoulli equation will expand lah. Okay, before this we just the first Bernoulli equation that we learn is P over rho G plus Z1 plus V1 squared over 2G equal to P1 P2 over rho G plus Z2 plus V2 squared over 2G. So there is no losses that we take into consideration. But after this, in this chapter, when we go to the last subchapter, the energy equation, this equation will change lah. Okay, there will be an extension of this equation, where we include the losses in the system. Okay, right. So in the piping system, let me allow first. Okay, in a piping system, so in a piping system, there are two losses. Okay, in a piping system, akan ada dua losses. Okay, I divide just to see clearly lah. If you write like this, maybe you ada orang suka lukis, kan? Cannot read a lot of sentence, like me. I also not that type of person. Okay, they will have one what we call as major losses. Okay, and another one is what we call as minor losses. Okay, so the summation of this, okay, the summation of this, both of these two losses, this will give you or give us the total losses lah in the system. Okay, so we need to add one major losses and the second one the minor losses. Okay, so what is the cause for the major losses? Okay, the major losses, okay, is caused by the friction. Okay, this the cause lah of that losses is friction. Okay, the geseran between the flow and the pipe, as we have discussed before, there is always a friction, and this friction will cause losses lah in the system. Okay, and minor losses, okay, this is due to the fittings or the piping system itself. Okay, in this case, if you see the figure, the diagram, so we have sharp edge entrance. Okay, we have the entrance from the reservoir to the piping. So we will introduce akan losses lah kat sini. Okay, and we know ada lagi ada elbow. Okay, from this pipe ada elbow. So this elbow pun akan introduce losses. Okay, we have 3 elbow, 2 elbow, 1, 2. So you will have losses, and you have a valve. So this valve will also akan introduce losses. And when the fluid is entering or exit, okay, through another reservoir or tank, so this will also have an exit losses. Ada entrance losses, ada exit losses. So all of these minor losses we need to calculate that as well. Okay, we will look after this lah. So the minor losses ni just to give you a clear picture is due to the system. Akan ada from the fittings, okay, from the valve, from the bands, this band, elbow bands, okay, from the elbows, from the teeth, from the inlets of the pipe, and from the exit of the pipe. Expansion, expansion if you have 2 different size of pipe. Okay, let's say you have 2 different size of pipe, one with a smaller pipe, another one is a bigger pipe, so you have an expansion losses here. Okay, and contraction when your 2 pipes different size again, and it flow from the bigger size to a smaller size. Okay, so you will have a contraction losses kat sini. Okay, so that's expansions and contractions lah. Okay, let me allow sekejap. Okay, so that's the general view lah of losses in a piping system. Ada major losses from the friction and minor losses from the fittings and whatever yang lain lah, bands, entrance, exit. Okay, so that's the losses in piping system. So we need to know how we can calculate the major losses and the minor losses. Okay, so when we have calculate these 2 losses, major and minor, and we will know the total losses in our piping system, and these losses can give us what is the pump power requirement to help this flow. But we know we have losses, so we need to add additional force from the pump to cover back lah the losses. Okay, so that we will have a pump lah inside our pumping system. Okay, so that's the reason why you calculate these losses, to give your pump the specific power requirement what you need, okay, in your system. Okay, so that's the general view. Okay, so this we are talking about the major losses. So this is major losses, okay, due to the friction. Okay, so the friction cause the pressure drop in the fluid flow, the major losses. And we know we have 2 different types of flow, and one laminar and one turbulent. Okay, for laminar flow, to calculate that pressure drop, okay, due to the friction, we can use this equation, okay, this first equation, okay, the delta P, okay, P1 minus P2, 8 times mu, okay, the dynamic viscosity, times L, the length of your pipe, okay, the velocity average, okay, we know the velocity of the fluid is not uniform, constant, so that's why they put velocity average, okay, so the velocity of the fluid divided by the radius of that pipe, okay, radius squared, okay, or we can write this equation in terms of diameter, okay, because we know R is D over 2n, okay, so that's why if you want to write in diameter, you can do that as well, so that's why you get 32 mu L times V over D squared, because R D equal to D over 2n, so if R squared will be D over 4, so this will be D over 4, and if you bring the 4 up at the upper position, that's why you get the 32 here lah, 8 times 4, okay, so you can use any equation, whether you want to use the radius or the diameter. So this is the equation when your flow is laminar, okay, that's why in the first chapter we learn about how we can calculate whether the flow is laminar or turbulent, from their Reynolds number, so from that, when you know that your fluid is laminar, so you can just use this equation to calculate your pressure drop, okay, so this is for laminar flow, remember, okay, laminar flow. But as the researcher or the physicists investigate more and more, this actually can be the equation for the pressure drop can be in one equation for both, for laminar, for turbulent, for circular or non-circular, smooth or rough surface, whatever flow, whatever pipe, we can calculate that pressure drop using this equation. So this is your main equation lah, okay, to calculate the pressure drop inside any types of pipes, any whether it's any type of geometry, whether it's circular or non-circular, okay, we just use this equation, so delta PL, so the pressure loss, PL ni pressure loss, equal to F is the friction factor, okay, we will look after this, okay, friction factor, okay, L the length, what do we say, the length of the pipe, okay, D is the diameter. Is it okay for you? Can you hear my voice?
Boleh je.
Kat sini ada construction sikit. So if it annoy you, just let me know. Okay, and times the rho of the fluid, whether it's water or oil or whatever, the velocity of the fluid, velocity squared over 2. So this is the equation that you will need to use to get your pressure loss, pressure loss, okay, pressure loss in your piping system due to the friction, okay, so far so good, will you follow, okay, in a piping system, okay, when you analyze a piping system, commonly we use the head loss and not pressure loss, okay, we use the term what we call as the head loss, okay, it's just not the same thing, but it's derivation from there, okay, we know the pressure, okay, kan pressure sini pressure sama dengan rho GH, okay, so the head loss, this is the general equation lah, so the head loss here will equal to pressure over rho G, okay, so this is H, okay, so if we divide the pressure loss by, so divide by rho G. So we will get the term what we call as the head loss. Okay, and this term, the head loss, is commonly used when we want to calculate the pressure, the major loss in the piping system. Okay, we will use the head loss. Okay, so just the pressure loss divided by the rho times G. So from this equation you will get F times L over D times V squared over 2G. So rho ni dah matilah. Rho ni akan di cancel out with the rho, and you have a G at the your denominator. Okay, so that's why you get this equation. Okay, the head loss of your piping system will equal to F, again the friction factor, times the length of the pipe divided by the diameter of the pipe, everything in standard unit, in meter lah. Okay, times the velocity squared divided by 2 times the gravitational constant. Okay, so this is the main equation lah. Finally, the final equation that you will use to calculate the major losses, okay, in the piping system. This major losses, okay, HL lah. Okay, when we want to calculate the major losses, we will use this equation. Okay, so there are another thing that is important in this equation. There are one main term, which is this F. Okay, what we call as friction factor, because we need to know that number when we want to calculate the head losses, kan? Okay, so this F, the friction factor or Darcy friction factor, because this person introduced this term. Okay, the equation, the real equation is this lah. Okay, 8 times the tau, the shear stress, over rho times velocity squared. Okay, but okay, we can use a much simpler equation. Okay, thanks to our old generation, where they investigate this, where they studied this chapter. Okay, the friction factor for a laminar flow, it is just 64 over the Reynolds number. So lastly, the equation will much simpler, very simple. It's just 64 over Reynolds number for laminar. Ni for laminar. We not go into the turbulence yet. Okay, for laminar flow, for your F kat sini, the friction factor, kat sini lah ni. When you want to calculate the head losses, you have to determine your friction factor, the Darcy friction factor, and this F for laminar is 64 over Reynolds number. You can know lah how we can derive this equation. Okay, if you want to know this equation, it's just a derivation from this equation, 32 mu times L, and ni delta P kan, delta P equal to 32 mu LV over D squared, and we have another term for delta P, which is this one. Okay, this is the second one. Okay, so delta P sama dengan F times L over D rho V squared over 2. So if you equate this equation, the first equation and the second equation, okay, you will get the F. Finally, you will get the F will equal to 64 over Reynolds number. This is Reynolds number. This is this mu over rho times D times V. It is 1 over RE kan. If you remember, to find the Reynolds number is rho times D times V over mu kan. Okay, so this is mu over rho times D times V, so this is 1 over RE lah. So that's why you got 64 over Reynolds number. If you want to prove this, you is from this lah, from this equation, these two equations, equation 1 and equation 2, and if you take F outside, you will get this 64 mu over rho times D times V, and this is equal to 64 over RE. Okay, so we know for a laminar flow, okay, we can calculate the friction factor using this simple equation 64 over Reynolds number. So that's why in the first subchapter we learn how we can calculate the Reynolds number. Okay, so that's the important why we want to know the Reynolds number, to calculate Reynolds number. Okay, any questions so far?
No, sir.
Tak ada? Okay, if you have, just ask me. Okay, we can answer any question if I can. If not, we investigate later. Okay, so that's settled for laminar flow Okay, for laminar flow, so your friction factor F, just using this equation. Okay, 64 over Reynolds number. Okay, but in turbulent flow, this is the common flow in your study in this chapter 4. Normally we were dealing with a turbulent flow. In real world pun normally the flow is turbulent. Okay, so we cannot use the similar equation for laminar flow. Okay, so we will use what we call as a Moody chart. Moody chart ni nama orang It's not your mood. Okay, I'm moody here. I'm moody today. Not it's name of person, Moody. Okay, he introduced or draw a chart where we can find the friction factor for turbulent flow. Okay, we will look here how this person get to draw the chart. It's very interesting story. Okay, I will show after this Okay, so when you have your friction factor value, the F, so you can put back in your head loss equation to calculate your head losses in your piping system. Okay, put back in this equation your F. Okay, so you have your the length of the pipe, you have the diameter of the pipe, you have the velocity of the flow. Okay, the velocity of flow you can calculate from the continuity equation. Normally they will give you the volume flow rate, and you need to find the V line from A times Vn. Okay, and divide by 2 times G, you will get the head losses of your piping system. And this head losses, the unit is in meter because head losses that flow have reduced because of the friction. Okay, the flow has been reduced to watt meter, and that number you can calculate how much power requirement that we need to give to our pump in order to get back the flow in the original height. Okay, so that's why when we have calculate the major losses, okay, we can determine the required pumping power. Okay, that because we have the losses in our system, so we will have a pump, okay, in our system, and this pump will give a power okay, will push the flow. Okay, so to determine this pumping power, you will use this equation. Okay, W dot, okay, pumping power in watt in watt. Okay, the unit will be in watt. Okay, watt watt. Okay, power Okay, to calculate the watt that you will give, the pump will give, is the equation, the Q ni tahu apa Q? What is Q? Anyone?
Volume flow rate.
Yes, so the volume flow rate, okay, your Q times your pressure losses delta PL you can calculate from your equation. Okay, when you have when you get the head losses, you can just times with rho G to get your pressure losses Okay, or you can ni apa salah ni ada ni typo, or you can write this equation in terms of, we know Q is equal to AV, okay, the area times the velocity, okay, and this delta PL equal to rho GH, okay, rho GH is the delta P times Q, and this Q, okay, times rho is the mass flow rate, and okay, we have a volume flow rate, mass flow rate equal to rho Qn in continuity equation. Is it right? Can you remember this? The mass flow rate, rho times Q. Okay, so that's why this rho times Q is mass flow rate. Okay, so that's why you get mass flow rate times G times the head losses that you have calculated from this equation. So this calculation, you will get your pumping power lah. Okay, when you calculate the losses in your pipe. Okay, boleh? Can you follow this from Q times pressure losses? You will get this one, because you know the pressure losses. Okay, delta PL equal to rho GH, rho GHL from this equation. Okay, that's why you rho GHL times Q, and rho Q is mass flow rate lah. That's why you mass flow rate times G times HL. That will give you your pumping power. Okay. Alright, any question before I move on?
No, sir.
Tak ada?
No, sir.
Sorry, saya panas ke ni, aircon lebih ni rosak. So sangat panas lah. Perlu sikit. Okay, so we have learned this. Okay, for laminar you just use 64 over Reynolds number, kan? But for turbulent, they said we need to use a Moody chart. Okay, what is Moody chart? Okay, so this is Moody chart lah. Okay, this is Moody chart. Moody chart. Okay, so this is Moody chart. In your exam or in your exam paper, they will provide you with this chart lah, right? So that you can refer. Okay, so the Moody chart actually comes from the Colebrook equation. Okay, Colebrook equation ni lah panjang ni. Okay, so this Colebrook equation were introduced by this Cyril F. Colebrook. Okay, so he the first man lah yang introduce this in 1939. Okay, he introduced that equation. This panjang ni kan, so Colebrook equation. That's why he names by the name is by his name. Okay, Colebrook equation, to find your friction factor here kan, this. Okay, from this long equation. So for turbulent flow, you can find your F through this equation lah. Panjang kan dia punya equation kan. Okay, so this equation, this sigma, okay, sigma. Okay, this is the roughness. Okay, this roughness, okay, of the material of the pipe. Okay, so they give you this table. If your pipe is made from glass or concrete or stainless steel or iron, whatever lah, copper, so you will get you can know the roughness of that material using this table. Okay, they give you the roughness in millimeter. So this is in millimeter. Okay, so the relative roughness ni sigma over d ni, relative roughness ni is the roughness over the diameter of the pipe. Okay, so that's why you need to, if they give you the diameter of the pipe in meter, okay, so you need to change the roughness, this in millimeter kan, 2 meter first. Okay, then you can calculate your relative roughness lah from this equation. Okay, but if they give you the diameter in millimeter, so you can just use the roughness in millimeter to get your relative roughness, because exam ni tak ada unit pun. Okay, it will dimensionless lah. Okay, so you will get that relative roughness, okay, from the material of the pipe, and you have calculate your Reynolds number in the beginning of the flow, whether it's then mostly this equation will give you turbulent lah. Okay, so this Reynolds number, let's say you get 5,000. Okay, 5,000, the value for Reynolds number is 5,000, which is turbulent. So you have this number and you have this number, so you can find your friction factor just using this equation lah. Okay, so because it is so long and susah lah, it's not straightforward. Okay, that's why the people keep study this Colebrook equation, and in 1942 Hunter Rose, another researcher, try to simplify this equation. So he came out with a graph. Dia buatlah graph. Okay, dia buat graph, tapi graph tu tak berapa cantik. Tak jadilah. Maksudnya orang still tak boleh nak use his graph to calculate the friction factor, to determine the friction factor for turbulent flow. Okay, so after he died, or mungkin tak mati aku, lepas tu 2 tahun lepas tu, 2 years after that, another researcher named Lewis Moody, that's why we call the chapters Moody chart, he found how we can determine the friction factor of the turbulent flow just using my chart. So he improvised this Rose chart, okay, where people still not recognize this chart. So he take this chart from Rose and modify and make it the exact chart lah, and much simpler. So that's why we get until now, 2020, we still use that Moody chart. Thanks for Lewis F. Moody, American researcher, who introduced this chart to us. And it's not just his work, it's very started from Colebrook, where he introduced the equation, and Rose tried to simplify that, and finally Moody found how we can use the chart to find the friction factor. Okay, so this is very menarik cerita dia kan. So saya rasa menarik lah. For me it is interesting how these three guys came out finally with a chart that we still use it until today, 2020, lama dah. Okay, alright, so this is Moody chart lah. Okay, where the Lewis F. Moody draw. Okay, in this chart, so there are three axes. So one is the friction factor, where we want to determine, okay, Darcy friction factor F. Okay, the second axis is the Reynolds number, okay, where you have calculated the Reynolds number, and last axis is your relative roughness, relative roughness, sigma over d. This is your relative roughness. Okay, so how we use this chart? Okay, in any question or problem, when you know that the material of the chart, the material of the pipe, okay, so they give you the pipe is made from stainless steel, for example, okay, and you already calculate lah the Reynolds number. Okay, you get Reynolds number equal to in this example, ni 10 kos 4, 10 kos 5, okay, 10 kos 5 30,000 lah, 30,000. So you get your Reynolds number equal to 30,000. Okay, okay. So to determine the F, the friction factor, so you know that your material of the pipe is stainless steel. So this is stainless steel, and the roughness that given in the chart is 0.002. So the roughness of the stainless steel is equal to 0.002 millimeter. Okay, 0.02 nilai kat sini 0.002 millimeter. And normally they will give you the diameter of the pipe lah. Okay, let's say they give you the diameter of the pipe is equal to 1. Diameter of the pipe is 1 meter. Okay, let's say, assume 1 meter. So you can calculate the relative roughness by using this equation. So your roughness of the pipe is 0.002 millimeter. So you need to change this in meter. Okay, so 0.002 divide by 1000. Okay, to get in meter kan, millimeter to meter kan, divide by 1000, divide by your diameter lah. Diameter of the pipe is 1 meter. Okay, 1. So you will get your relative roughness is equal to 0.002 bahagi 1000 bahagi 1. Okay, you will get 2 times 0 to the power 10 to the power minus 6. Okay, or this is equal to 0.000012345 panjang sangat maybe my example is not right lah the diameter ni should be much smaller lah because if you get this let's say I put this one so 0.0001 2 3 4 5 6 2 so this value is not even in the chart pun the smallest is 0.00001 so this our my example ni is not right example lah so I cannot use the diameter one lah. Let's say diameter is of the pipe besar ni sentimeter ni besar sangat tak logik lah so let's say is berapa nilai paling sesuai 5 cm okay 5 cm okay 5 cm okay diameter of the pipe is 5 cm okay so in meter will be 5 bahagi 100 0.05 lah okay 0.05 meter okay so when we divide by 0.05 okay you will get 0.002 divide by 1000 divide by 0.05 so you will get okay this must logic lah you will get 4 times 10 to the power minus 5 okay so this will be 0.000 1 2 3 4 5 okay okay dapat so this is your relative roughness so you get your Reynolds number when you calculate you get 30,000 and you get your relative roughness equal to 0.0004 so what you do from this chart is okay find the Reynolds number first okay 30,000 kat sini okay so this 10 power of 5 so this this 1000 10 power of 3 power of 4 power of 5 so your 30,000 kat sini lah okay 3 times 10 to the power of 5 so this is 30,000 so this is your Reynolds number okay so draw a line upwards and your relative roughness 0.0004 is somewhere okay, this here lah this is 0.0005 this is 0.001 so your 4 kat sini lah betul 0.0004 so you draw another line from this value okay and that intersection okay this intersection of your line okay for this number for your relative roughness so you can go to the left and you can get your friction factor berapa kat sini okay can you follow that
Yes sir, boleh.
Okay, so depends lah, depends on your Reynolds number and your relative roughness. So you will draw two lines, okay, one for your Reynolds number and another one for your relative roughness, and that intersection you go again until your to the left, and you will get the friction factor number lah kat sini. In this case, in this diagram they have 3000 and they have the Reynolds number relative roughness to 0.008. Okay, so they draw another line kat sini, and this intersection they draw sampailah hujung, and this kat sini ni dia dah akan dapat the friction factor for this flow. Okay, so that's how you use the Modi chart, okay, to determine the friction factor. Okay, so we don't have to use this long equation, okay, for this too messy kan. Okay, you can just you can determine the friction factor just using the Modi chart. It is much simpler, it's much easier lah. Okay, alright. Okay, ada soalan? Siapa-siapa yang tak faham atau apa-apa nak tanya, you can ask now, because you will use this Modi chart when you want to solve any problem in regarding turbulent flow, because you need to find the F, the friction factor. Okay, ada soalan before I move on? Tak ada. Okay, so I hope you understand how you use the Modi chart to calculate the friction factor. Okay, so that is major losses lah. Okay, I've said in the beginning, you have two losses in the piping system. One major losses, okay, due to the friction. So we finish this one, okay, for both laminar and turbulent. So the next losses in your piping system is what we call as minor losses. Okay, so these losses is due to dah cakap tadi kan, due to fittings, valve, bands, elbows, teeth, inlets, exits, expansion and contraction, okay, in your system. So that's the cost for the minor losses. Okay, so so you have a lot lah. If your piping system is big, okay, so you will have a lot of connections, so you will have a lot of fittings, a lot of valve or elbows, so you need to calculate each of that minor losses, and when you add these minor losses and the major losses due to the friction, you will get the total losses of your piping system. Okay, and minor losses, okay, usually will express in term of loss coefficient, KL. Okay, so in the question they will give you lah the KL of anything. Like for example, we have seen last Sunday, okay, for this one. So that's why they give you the K pipe for entry, the loss coefficient, the minor losses coefficient for the pipe when it enter the pipe kat sini. Okay, when the reservoir enter the pipe, they will have losses. So this minor losses what we call K pipe entry. Okay, and they have also losses when they exit. Okay, exit the pipe to the reservoir kat sini, exit. Okay, you have another losses, another minor losses. Okay, and you have a valve, globe valve, 1 globe valve, 2 globe valve, and 3 globe valve. So they give you the minor losses coefficient for globe valve, okay, 1.9. And you have a check valve. So check valve pun ada minor losses juga, okay. So they give you the minor losses coefficient for check valve, 3.0. And you have elbow, a bend, 1 band, 90-degree band, 2 and 3 bands. Okay, this band will introduce losses. Okay, so they give you the coefficient for that 90-degree band equal to 3. Okay, so you need to calculate lah all of these minor losses, enter from the globe, from the elbow, from the check valve. So this will give you the minor head losses. Okay, and to calculate the minor losses, you will need to use the equation this one. Okay, the minor losses equal to the coefficient of the losses, okay, loss coefficient KL times the velocity squared, okay, the velocity of the flow, okay, divide by 2 times G. Okay, so this is much simpler lah compared to the major losses kan. Major losses you need to find the friction factor kan, so that's lagi panjang. But minor losses, you just simple equation, loss coefficient KL times velocity squared over 2G. Okay, so if you have a constant diameter of a pipe, so that means your V is the same lah. Okay, but if you have two different cross section area of the pipe, so that means you need to separate for pipe the bigger pipe and the smaller pipe, because the velocity is not the same kan. Velocity of the fluid inside the bigger pipe and the smaller pipe will be different, so you need to calculate separately for bigger pipe and for smaller pipe. But if you have a pipe with a constant diameter, so that means your velocity throughout the pipe is constant, is the same, so you don't have to separate that. Okay, can you follow that? Boleh
Boleh sir.
Boleh. Okay. Do we need a break first? 5-minute break boleh? Before I move on.
Okay sir.
Okay. Okay, we take 5 minutes first, because some of you give a feedback to the feedback form. They said it's nice if we have a 5-minute break. I agree with that. So that's why we take a 5-minute break first, and 11 o'clock we continue back. Okay. Alright. So just 5 minutes bukannya 15 minutes Okay, we continue back our lesson. Okay, semua dah ada kan?
Ya, sir.
Ada. Right, so we go back to our slide. Okay, so the minor losses. Okay, so that is the minor losses. Okay, the losses from all the fittings, valve, bands, inlets, exits. Okay, so you need to add that losses in every losses in each of the fitting, valve, everything. So that will give you the total minor losses. And when you add minor losses with major losses that you calculated before, so that will give you the total losses lah. Okay. Okay, why we have this minor losses? Okay, maybe some of you curious why we have these losses in the pipe. Okay, let's say the pipe inlet. So this pipe inlet and this pipe exit. Okay, when the pipe from the reservoir goes into your pipe, okay, so you will have losses because of this connection lah. They will have flow yang tak masuk sepenuhnya. So you will see that if you do simulation. Okay, so that's where you have the pipe inlet losses. Okay, and this is depends lah whether your connection from the reservoir with your pipe is a sharp edge. Okay, this like this 90 degree. Okay, or your edge is rounded. Okay, the smooth round. So that's your flow can flow from the reservoir to the pipe smooth lah. Boleh masuk secara smooth. So that's why your the loss coefficient from the rounded compared to sharp edge is much smaller. But the losses is reduced, is minimized. Okay. Similarly, when you have the pipe exit, okay, from the pipe to the reservoir, it will have akan ada lah turbulent dia yang flow tu, macam ni. Okay, that's why you have the losses, and this will depends on your geometry of that connection, okay, whether it's sharp edge or rounded. Okay, so that's example of inlet and exit, and this is expansion, like I draw before. When you have a smaller pipe, okay, goes into the bigger pipe. Okay, so your flow from here, from left to the right. Okay, when this flow comes to the bigger pipe, you will have a turbulence macam ni. So this will give you the losses. Okay, so that's why you have the expansion losses lah. Okay, expansion losses kat sini. Okay, so you will calculate the expansion losses for this bigger pipe, because dia masuk kat sini kan. So it will corresponding to the bigger pipe lah. Okay, so when you calculate, you will use the diameter of the bigger pipe, not the smaller pipe. Okay, for expansion. For contraction, the opposite of this. Okay, when your flow is coming from the bigger pipe to the smaller pipe, okay, so you will introduce this turbulence juga. Okay, and this will give you losses. Okay, so you can calculate these losses lah through the equation. So that's why you have the coefficient of losses for expansion and also for contraction. Okay, so that's why you have that losses. Okay, sama juga through the band. Okay, whether it is a 90 degree band, this is smooth band. Okay, the band is smooth, rounded, compared with this meter band. Okay, sharp meter band. Okay, 90 degree. Okay, that's why you have, when this fluid flow, they will collide with this first kan. This will give a turbulence, that will give you losses lah. Okay, not every flow smoothly goes here kan. Because compared to this smooth band, okay, you will have smooth band and less colliding with this wall compared to this 90 meter band. That's why your coefficient is higher compared to the 90 degrees smooth band. Okay, and if you add meter band with vein, ada vein ni, so this vein will help lah the flow to flow macam tu kan, akan flow ke bawah macam tu. So that's why it reduce the loss coefficient is reduced. That's why you have only 0.2 because it helps the flow from this horizontal flow to the vertical flow. So this vein will help that. Okay, that's why with veins you have only 0.2. Without vein is 1.1. It's higher coefficient, loss coefficient. Okay, similarly for 45 degree ada coefficient, ada loss coefficient dia. For this return band 180 return band ada loss coefficient dia. And this T junction, okay, you have your loss coefficient. T line flow ada juga loss coefficient, and threaded union ada juga loss coefficient. So that's why you have that loss coefficient because of the flow not 100% move without the friction lah. So that's why you have that loss coefficient, and normally they will provide you the loss coefficient in the question. You just use that coefficient to calculate in the minor losses. Okay, so valve pun ada globe valve, this is the coefficient, angle valve, check valve, ball valve, depend lah on what valve they use in your pipe, in the piping system. And they can be the valve can be fully open or fully closed. Kalau fully closed ni memang tak lalu lah kan. If the valve is fully closed, then the flow cannot flow. That's why maybe it's quarter closed, so you have a loss coefficient 0.3. Half closed, so that means you have more friction. For you, the valve goes deeper kan, so that's why the loss coefficient is higher. Okay, 2.1. If you close 3/4, lagi banyak awak ke dalam, the valve goes try to block the fluid, that's why you have a loss coefficient higher lah. Okay, that's why it depends on this whether it's fully open or quarter close or half close, third quarter close. Okay, so this information will provided lah in the question. Okay, so that's why you have these minor losses in your piping system. Okay, so to calculate the total head loss, okay, in your piping system, as I said, you need to add both of that losses, major losses plus the minor losses, will give you the head loss, the total head loss lah. Okay, from the equation that you use for major, okay, this equation, and the equation for the minor losses. Okay, this is if you have a different diameter. You need to, that's why you have Li, Vi, depends lah. If you have two different diameter of pipes, so you need to calculate first for the L1, calculate the major losses and the minor losses, and for the number 2, the pipe number 2, so you need to calculate the major losses and the minor losses. So you add up everything, that will give you the total losses. But if you have the piping system, the entire piping system is constant diameter, only one diameter, same diameter, so you can just use the equation straight away. Okay, because the V will be the same, so that's why they take out the V outside. Okay, so this is much more simpler equation lah. Okay, alright, any question? Before I show a few example how we can calculate the head loss. Ada soalan? Tak ada soalan? Ha?
No, sir.
Tak ada Okay. So I show you a few example. Okay, how we can use chapter 1 and 2 to solve any problems lah. Okay, in this first example, they said water at 5 degrees, so they gave you the rho 1000 kg per meter cube, and the dynamic viscosity, so they gave you the dynamic viscosity is flowing. Okay, this is water flowing steadily through a 0.3 centimeter diameter. So the diameter of the pipe is 0.3 cm. Okay, and 9 meter long. The length of the pipe is 9 meter. So this is the D. Okay, at an average velocity of 0.9. So this is the V. Okay. So determine the head loss. So they ask you to determine the head loss, okay, the pressure drop and the pumping power requirement. Okay, the head loss ni itulah major plus minor, both if there is, but in this case there is no minor losses. So just only the major losses due to the friction, because only the pipe tu macam apa, satu pipe je. There's no fitting, there is no valve, there is no connection, so that's why you don't have the minor losses. So that's why they did not give you any minor loss coefficient. Okay, so to do this, first step is you need to calculate the Reynolds number. Okay, first calculate your Reynolds number, because you want to determine whether this is a laminar or turbulent. Whether it's laminar flow or turbulent flow. Okay, that's why it shows here the first step. Okay, so you can calculate the Reynolds number through this equation, rho times V times D over mu. Okay, the rho is 1000, they give you the rho, times V 0.9, okay, times D 0.3 centimeters. So you need to change this in meter, divide by 100. Okay, so you get 0.003. Okay, divide by mu, your dynamic viscosity, 1.519 times 10 to the power of minus 3. So you will get the value for Reynolds number is 1777. So because of this is less than 2300, so that means your flow here is in a laminar condition. So because it's a laminar condition, you can use the simpler equation to find your friction factor, which is 64 over Re. Okay, so you have 64 over Reynolds number 1777. So you get your friction factor 0.036. So you don't need to use the Moody chart, okay, or the Colebrook equation. Okay, you just get from this because it's laminar. Okay, you can just use this equation to find your friction factor. Okay, so after you get your friction factor 0.036, you can use this head loss equation, because they ask you to find the head loss, okay, the head loss. Okay, this equation, F times L times V squared over D times 2G. Okay, so you have your F 0.036, you have your L, the length of the pipe is 9 meter. You have your V 0.9 squared, so that's 0.9 squared, divide by diameter in meter. Okay, don't forget to change any not standard unit in the standard unit. So they give you the diameter in centimeter, so you need to change that in meter. So diameter is 0.003 times 2 times G, 9.81. So you get the value for your head loss is 4.46 meter. Okay, so this is the height that has been reduced. Okay, so you need a pump to provide this additional height to make sure the fluid flow in the pipe fully internal, dia penuh dengan air dalam pipe tu. Okay, so when you get your head losses, okay, they ask you to find the pressure drop as well. You know that pressure drop and delta H ni, H loss ni sama dengan delta P over rho G kan. Okay, from the equation. So to get delta P is just a multiplication of 4.46 with rho times G lah. Okay, or in this example they show you from the real equation. We know that before kat sini, and this kat sini here. So this delta PL equal to rho F times L over D times rho V squared over 2. Okay, But this is just to get this, you can just multiply by rho times g je, kan? Sama juga kan? You don't need to to write this equation. You can just use 4.46 here, the HL times rho times g lah, kan? You get 4.46 times rho 1000 times 9.81. It should give you the same answer lah kat sini, 43.7 kilopascal for 4.46 times 1000 times 9.81, and this is 43.752 or 43.7 lah kilopascal. This is pascal. So just the same thing lah, but in this example they show you how the real equation. You can use this equation, okay, or you can just multiply by rho times g. It's much simpler. Okay, so this settled for heat loss and the pressure drop and pressure loss. Okay, so the next question, they ask you to find the pumping power requirement. Okay, we know that the pumping power requirement, the equation is this. They use V dot ni Q lah. Kalau I use Q kan, in my teaching I use Q. This is Q lah. It's just the same thing lah. Okay, don't want to confuse you. What is V dot? Is a Q. Okay, so the volume flow rate is the velocity times A. So you have the velocity of the flow 0.9, and they give you the diameter, so you can find the area of this pipe area. Okay, pi r square or pi d square over 4. Okay, in this example pi d square over 4. Okay, 0.9 times pi times 0.003 square over 4 for the use diameter, you get your volume flow rate. Okay, 6.36 times 10 to the power of minus 6 meter cube per second. And when you get that Q, you can find your pumping power requirement from this equation. Q times your pressure drop, okay, pressure loss. Okay, you have calculate here the 6.36 times 10 to the power of minus 6 times 43,740. So you will get your pumping power requirement in watt, 0.28 watt. Okay, so this pump will provide 0.28 watt, okay, to overcome the losses lah in your pumping system. Okay, ada orang masuk. Okay, so that's how we use the equation from the Reynolds number equation to the head losses, and you can find your pumping power requirement after that. Okay, any question regarding this example? Ada soalan? Ada orang tanya kat chat ke? Tadi kat chat tu ada orang tanya ke tu link je? Okay, I assume. Okay, this is simpler ni lah, simple example lah, because this laminar flow and only one pipe, only just that pipe tu only that portion je, so it's much easier lah. Okay, but in your exam, your pipe tu much more complicated lah. You have, if we look at the example before, you have the pipe tu macam ni kan, ada ada a lot of connection, so you need to calculate that minor losses lah. Okay, and you have to find the major losses. Okay, so it is much more complicated compared to this example. So this example is very simple lah, just one pipe and similar size and similar cross sectional area, so it's just simpler. Okay, maybe we can look one more example from this equation. Okay, this one. Okay, so so water supply system for a building is shown here. Okay, the flow rate of water being pumped is 10 liter per second, so your Q is 10 liter per second. Okay, So you can change this in meter cube per second later. So 0.001 meter cube. You will get your Q equal to 0.001 meter cube per second. Okay. Alright. Through a 60 meter long, so your pipe length is 60 meter. Okay. And 0.15 meter. So your diameter of the pipe is 0.15 meter. Okay. And it is a galvanized iron pipe. So this is the material of the pipe. It's a galvanized iron. Okay. So they give you the minor losses coefficients for the pipe fittings used are. So they give you the loss coefficient for pipe entry. That's ini entry 0.5, and they give you the pipe exit. That's ini 1.0, and the globe valve. Okay, these three globe valve, you have the loss coefficient equal to 1.9, and you have a check valve equal to 3, and the 90 degree bend 1, 2, 3. You have the coefficient is 3.0. Okay, so they ask you to determine the flow condition of water in pipe, whether it's laminar or turbulent. So this is easy. So you can just use your Reynolds number equation. Okay, we have done this last Sunday, and I show you how to calculate this. Okay, you just use this equation. Okay, you need to find the velocity first. Okay, from the Q. Okay, Q is 0.01 divided by the area of the pipe, pi times r squared, 0.15, 0.075 squared. Okay, so this will give you the velocity of the flow, 0.01 divided by pi times 0.075 squared. So this is 0.0.56 meter per second. Okay, you can calculate your Reynolds number through this equation. The rho of the water is 1000 times the V 0.566, okay, times the diameter of the pipe is 0.15, okay, divided by mu. Mu is where is the mu? Oh, here, 1.31. Okay, 1.31 times 10 minus 3. Okay, so you will get the Reynolds number, and you can determine whether it is laminar or turbulent. Jadi 1.31. So you get 64,000. 64,809. So this is turbulent. Okay. Okay, so you settle for number 1. And they ask you to find the friction head loss. Okay, the friction head loss, the major loss lah. The major loss is the friction loss kan. So you need to find the major losses. Okay, how we can do this? Through your equation. Okay, HL equal to F times L over D times V squared over 2G. Okay, so this is turbulent, so that means you need to use a Moody chart to find your F. Okay, first from the Moody chart. Okay, from the Moody chart, mana Moody chart? Okay, mana Moody chart? Okay, here. So they the material tu apa tadi? Material dia ialah galvanized iron. Galvanized iron. So you look from your your chart. The galvanized iron is 0.15. The roughness is 0.15. Okay. So that's your roughness for this pipe. So roughness is 0.15 millimeter. Remember, it's millimeter. And your D, the diameter of the pipe, is 0.15 meter. So D is 0.15. So to calculate your relative roughness, this one, relative roughness ni, so you can calculate 0.15 divide by 1000 first, and divide by 0.15, the diameter. Okay, so you will get 0.15 divided by 1000 to change in meter, and then divide by 0.15. So you will get 1 times 10 to the power of minus 3, or this is equal to 0.001. Okay, so this is your relative roughness, 0.001. And let me erase this first. Okay. Auto erase ni. Auto erase pula. Tak apa. Okay, so this your 0.001 is kat sini, so this is your 0.01. Okay, and your Reynolds number you calculate is equal to 64,000. Okay, so this is 1, 2, 3, 4. So 6.5 lah, 6.5 10 power of 5 kan. Okay, so you refer back your Moody chart. 10 to the power of 5 kat sini, and it's 6.5. Okay, this is 10 power of 5. Saya zoom sikit. Okay, so your 6.5 is somewhere here, kat sini kan. Okay, this is 8, 7, 6, so 6.5 in the middle. If you go draw a line upward and intersect with your line with 0.001 kat sini, line kat sini intersect dengan 6.4 somewhere, 6.5 somewhere here, and you go until the end. Okay, and if you do that, okay, you will get this the friction factor equal to 0.023 somewhere here. Okay, 0.023 is 254 kat sini. Okay, this is the intersection of your 6.5 ini dengan 0.01 kat sini, and if I take here sampai hujung 0.002 lah. If when I did it properly, I get 0.023 lah. Maybe my line is not too precise. Okay, so you get your F equal to 0.023 from the Moody chart. Okay, so then after that you just put back, so you have your okay, so your F equal to 0.023. Okay, so you can put back in this equation to find your major losses. Okay, F, major losses, F is 0.023 times the length is 60 meter, times the velocity squared, velocity is 0.566 squared. Okay, because of this pipe is a constant diameter, tak ada yang pipe yang smaller or bigger each other, so that's why you can just use the velocity here lah. If there is two different pipe, so you need to find one by one. Okay, because this example you have only one constant diameter, cross-sectional area, so that's why you can just use the velocity here. So this velocity squared over d, the diameter 0.15 times 2 times g, 9.81. Okay, so this will give you the the major losses lah, and the friction head loss. Okay, 0.023 times 60 times 0.566 square over 0.15 times 2 times 9.81. So you get 0.15 meter. So this is your answer for head loss lah, friction head loss, the major loss. Then they ask you to find the minor loss, the minor head loss. Okay, so this is the yang apa, HL equal to this HL minor, so KL times is it V squared? Minor losses is KL times V squared over 2G. Okay, so that's your equation for minor losses. So KL times V squared over 2G. So you need to add everything, every loss that you have. Because it's summation, summation of KL. Okay, V squared over 2G. So this is, first you have your entry pipe loss coefficient, so it is 0.5. So ada satu je, so 1 times 0.5. Okay, then plus you have the exit loss. Okay, satu juga exit loss, so times 1 times the coefficient is 1. Okay, plus, so you have a globe valve loss coefficient. You have 3 globe valve, 1 globe valve, 2 globe valve, 3 globe valve. Okay, that's why you need to 3 globe valve times the loss coefficient 1.9. Okay, plus you have check valve. Okay, 1 check valve times the coefficient is 3. Okay, and lastly you have 3 bend, 3 90-degree bend. Okay, plus 3 times 3. Salah apa? Okay. So 3 times 3. 3 times 3. Okay. Add all of these loss coefficient, then times with your V squared. So V squared is 0.566 squared divided by 2 times 9.81. Okay, so this is your total minor loss. Okay, 1 times 0.5 plus 1 plus 3 times 1.9 plus 1 times 3 plus 3 times 3, then times the velocity squared 0.566 squared over 2 times 9.81. So you will get the minor loss, the minor head loss, equal to 0.313. Okay, so this is your minor head loss in pipe. Okay, and lastly, to find your required pumping power, you need to add this both loss, 0.15 and 0.313. So this is your total loss. The total loss will be equal to 0.15 plus 0.313. So this will equal to 0.5 plus 0.313. So you will get 0.463. So your total H loss. Okay, and to find your pumping power, okay, this is equal to equation there. It is, we check back. This is the Q. So we have the HL. So rho times Q times G times HL lah. Okay, rho times Q times G times HL. Okay, we have the rho 1000, we have the Q 0.01, we have the G, we have the HL. Okay, so you calculate this. Rho 1000 times Q 0.01 times HL times G 9.81 times HL 0.463. Okay, and we multiply all of this. 1000 times 0.01 times 9.81 times 0.463. So we will get the answer for the pumping power is 45.4 watt. Okay, so this is your D. Alright, any question? Ada soalan? Senyap je semua. Any question?
Tak ada sir, no.
No sir.
So yang nilai K tu memang ikut yang tetap yang dah bagi dalam kotak-kotak saya tu.
Nilai K ni yang ni yang dia bagi dah soalan ni.
Memang fix macam itu je.
Dah bagi dah, guna je lah. This value you mean?
Yes sir.
Just use this value lah. Don't make up your value. They gave you the value, so just use this value. Kalau soalan ni pun dia bagi jugalah. K pun ada sini. K apa for elbow, K for 45 elbow, K for valve, kick valve, K for contraction. So they give you the value, so just use that value in your calculation. Okay? Any other question?
No sir.
Then, okay. I hope you get the concept, or you understand how we can calculate the losses in the piping system. Okay, and how we can calculate the required pump power. Okay, from that loss. Okay, so that's why in the real piping system you will have a pump lah. To provide that additional power to cover back the losses. Okay, so this is another example. I think you can do this on your own. Okay, and this is lain sikit sebab dia ada dua pipe yang berbeza size. Okay, so one with 60 meter length with the diameter 0.289 and another one is 22 meter with the diameter 0.194. So ada pipe yang besar, ada pipe yang kecil. So when you calculate the losses, you need to calculate one by one. You need to calculate the major losses for pipe 1 and minor losses for pipe 1, and you need to calculate the major losses for pipe 2 plus the minor losses for pipe 2. So that's the difference lah between this question and this question. So because this question is just the pipe is a similar constant cross sectional area. The diameter is the same. So that's why you just tambah je lah semua. The V you can use the V that you calculate from the flow rate, the volume flow rate. But in here you need to calculate you have the different diameter, different area, and you have the Q. So you need to calculate the V1 and V2 lah, each for each pipe. Okay. Right. So this I leave to you to do at your own time. Right. And next week, okay, because Sunday is a public holiday. So next Tuesday lah. So next Tuesday we will finish the last chapter, which is the steady flow energy equation. So this is the last one. Okay. Ini pun related lah to your to the losses. Okay. And we will do tutorial as well. We will show question, past year question, and we can do it together lah. Okay. Alright. So if there's no more question, I think I can end the class. Okay. Thank you very much for your attendance. Okay. Don't forget to fill up the attendance form. And okay. So we meet again next week lah. So have a nice holiday, long holiday kan, long weekend. We meet again next week, insyaAllah. Okay, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam sir. Thank you sir.
Waalaikumsalam sir. Thank you sir.
Thank you, sir.